All right, hi BC Calculus. This is the first of many screencasts that you'll be listening to this year. One of the things that I'm trying to do, given our new normal this year, is just try different things, different ways to make that 70-minute period for you all. I'm aiming for enjoyable. That's my goal. I'm aiming for enjoyable. But it's tough when my students can't move around, when you can't go up to the board, when I can't see your faces, all these things. So I'm just trying different things to see what works. So one of those things that I'm trying is this idea of, it's called flipping something, flipping an instruction, right? So in this screencast, we're going to learn a new topic, brand new for TIC, okay? And for AB students, as we enter this very early period of AB content, your job here is to take full advantage of this time where you are really reinforcing stuff that you've seen before already. And then also in class, playing it kind of cool by dangling little things by your TIC cohorts, but not ruining the surprise. The last thing you want to do is tell someone how the movie ends, right? Like, who would want to go up to someone and say, oh, by the way, she dies? Like, you just ruined the whole experience to me, okay? So this new topic here is called a slope field. What is a slope field? Well, a slope field is exactly what it means. It is a field of slopes, okay? What does that mean? Well, let's see what happens, okay? So slope fields, when you are given a slope field, you will often be given what looks to be kind of an empty coordinate plane, like what you see right here, right? And you'll see these kind of dots sometimes. And unless we're told otherwise, we want to assume that these dots here are at lattice points, which are points where the coordinates are integers, okay? Accompanying a slope field is often a differential equation, okay? And I just made one up and gave you one here. I gave you a very simple one. dy dx is 1/2 x. And then you'll see below, I kind of made a t-table. And I'm wondering, what does dy dx equal at these various x and y points, right? And maybe you're looking at this part, you're saying, well, Miss Yam, you're saying, you're saying you want to evaluate dy dx at these xy points, but when I look at dy dx, it's only in terms of x. So why did you vary the y variable? The y variable will not vary the dy dx at all. And you're absolutely right. That's definitely the case in this differential equation. I'm just leaving it open for the possibility that, maybe we can have a dy dx that has x and y, and the y will matter, right? So I'm just maybe being a little bit superfluous here. So what we're going to do, before we actually get to the answer of what exactly a slope field is, what does it tell you, why is it useful, let's just fill in the t-table, okay? I'm going to go ahead and fill in the t-table. I'm going to input in these values of x and y, or just x in this case, and evaluate dy dx at these values. And you go ahead and then replay me when you have filled in your t-table. Okay, so here's my t-table. You can double check with yours and make any kind of minor adjustments that you may need to make. Now, what do we do with this? All right, well, let's see. I'm going to go and I'm just going to focus on this point right here at 1, 0. At 1, 0, dy dx equals 1/2. I'm going to come over here to my coordinate plane. I'm going to find the point 1, 0, which is right here, right? Find the point 1, 0. 1, 0 is right here. And at this point, I'm going to put a little tangent line, a little line whose slope is 1/2. So right here, I want to put a little slope segment at 1, 0, whose slope is 1/2. So let's see. Up 1 over 2. So I want this to be my slope. I'm just going to go boink right there. Look at that. I got a little line segment at 1, 0 where the slope is 1/2. Then I'm going to go up here. I'm going to look at this over here. At 0, 0 here, 0, 0. I want a little line segment with a slope of 0. Okay, I'll use the color. Here we go. Boom, right there. What I'm going to have you do here is fill in, or I should say, graph the rest of these dy dx's. Okay, I'll do a few with you. Let's take a look at 0, 1, 0, 1, slope of 0. I'm going down here at 1, 1, slope is 1/2. So I'm eyeballing it, boom. At negative 1, 1, the slope is negative a half. Let's see, up 1, left 2, something like that. And let's see, 1, negative 1, 1, negative 1, I'm at a half. 0, did I miss a point? Negative 1, 1, 1, negative 1, oh, negative 1, negative 1. I've got what, negative a half? Nicely done, everyone. Really good. 2, 2, 1, 2, 2, 2. Ooh, okay. At 2, 2, the slope is 1. It's a little deeper, right? I want to make sure that visually I'm paying tribute, negative 2, negative, with relative accuracy. You know, when someone's looking at a slope field, will someone ever kind of like go and take a little ruler and say, uh-oh, I don't know, Annabelle, this slope is not exactly a half? But no, it's never going to be that. Okay. So what I've done is I have filled in this coordinate plane with little slopes. Okay. Now you see why this field here is called a slope field. What I'd like you to do, I'm just going to extend my t-table, okay? I'd like you to evaluate the slope field at these additional points. I'm going to put it in green here, just so we can fill in, not the whole coordinate plane, but at least let's fill in the gap at these points here, okay? So what I want to see you do is evaluate the slope field at, let's see, let's add the point 2, 0. Let's add the point 0, negative 1. Let's add the point 2, negative 1, 2, negative 1. Let's add the point, is that 1, 2 at 1, 2. And let's add these other green points here, okay? You can find those ordered pairs, and I'll meet you after you've found those slope values and you've put in the little slope segments and replay me. Okay, so I think you're going to see here, if you want to look at my t-table, I just did the points in green on the right-hand side. I wrote those out here. I'm going to trust that you were able to, on your own, write these points out and find those slopes. Now, if you look back at this for a second, right, if you look at this slope field now, this is now what's called a completed slope field. And the reason why it's completed is because I evaluated dy dx at all these values. Okay, I evaluated dy dx at all these values, and I went and kind of put in these slope segments. This is now a completed slope field. And I think some of you may see where I'm going. AB, you obviously know where I'm going, and you're gonna, express nothing but surprise and glee. Okay, and I know Porter and Annabelle, you two are actors, so I expect nothing less than like absolutely convincing Emmy performances here. If you look at these dy dx's, well, let's have a conversation here. Dy dx is what? Dy dx is the slope of the line tangent. And if you look at this here, if you look at this collection of tangents to some curve, I hope you kind of see that the curve looks like this. There's kind of like the ghost of a parabola is back here. And it looks like it could be a parabola shifted up or down, right? If you kind of zoom back. And it looks to be that, dy dx equals 1/2 x is giving you a sense that if you look at the field of slopes, you can glean what actually y, or the function of x, is. Now here's the first time you're going to get a taste for going backwards. Take a second here. This is really for the TIC folks. Dy dx equals 1/2 x. What's a possible y? So what y would give you a dy dx to be equal to 1/2 x? So in other words, 1/2 x is the derivative of what? Really important that you stay with me here and pause me, and just give it a thought. And then replay me when you have a thought. Okay, here I go. When I think about what y could be, I'm thinking, the derivative of something ends up being 1/2 x to the first. So I'm going to start with kind of doing the power rule in reverse. Maybe it's x squared. It's x squared, right? Let's think. It's x squared. The derivative of x squared is 2x. I want it to be 1/2 x. Oh man, so what do? The derivative of x squared is 2x, and I want this to be 1/2 x. Maybe there's a coefficient in front. Let's see. Let's say if it's 1/4 x squared. Look at that. Here we go. If y equals 1/4 x squared, dy dx is 1/2 x. We being TIC are so used to going this way from the function to the derivative. Now begins the second half of AP Calculus, which is the task of going backwards. Okay? I'm going to add these words in a minute. I'm going to speak them first. When we've gone this way, we have differentiated. When we go this way, we are anti-differentiating. Okay? And when we go, let's do this again. When we go this way, we are taking the derivative. When we go this way, we are finding the antiderivative. Don't write those words down, just soak it up right now. Soak it up, okay? Right now, the words don't matter. I will give you all the vocabulary you need in a day, okay? And maybe you're feeling kind of like sly and you've had a good meal and you're kicking back and you're thinking to yourself, well, wait a minute, Yam, why couldn't this be 1/4 x squared plus 5? Because the derivative of a constant is 0. And guess what? If y equals 1/4 x squared plus 5, dy dx is still 1/2 x. And then maybe, Braden is saying, well, I can one-up you there. Well, how about y equals 1/4 x squared minus 17? Yes, it can be minus 17. And then maybe Madison, she's quiet, but she has some pretty scary thoughts. Maybe she's saying, why couldn't it be 1/4 x squared plus 20,000? And it could be that too. In fact, really, when you think about it, y, the function, could be 1/4 x squared plus any constant. I'm going to write down here and say, well, actually, y could be 1/4 x squared. And I'm going to say to the reader, plus c, okay? Plus c, where c can be any constant. Okay? Now let's come back and have a conversation about this slope field. Well, let's see. What if the c value was y equals 1/4 x squared plus 0? Well, watch this. If y equals 1/4 x squared plus 0, you want to know what that curve would look like? Watch this. It looks like this. Let me get a nice, here we go. It's going to look like this. Watch, watch. You ready? Ready? It's going to look like this. Well, y equals 1/4 x squared plus 0. It's going to look something like this. There's my curve. Okay, if it was y equals 1/4 x squared plus 2, what will it look like? Y equals 1/4 x squared plus 2. Actually, I should really fix this branch here. This branch is a little bit off. Here we go. Let's go back and do that one nicely so you can see it. Okay, y equals 1/4 x squared plus 0. I'm just redoing that because I'm not happy with my artistic rendering. Okay. Here we go. Y equals 1/4 x squared plus 0. Y equals 1/4 x squared. Did I say plus 2 or plus 1? I don't remember. Let's just do plus 1, I guess. Y equals 1/4 x squared plus 1. It'll look like this. What do you notice, everybody? What do you notice? You notice that these curves, the antiderivatives, if you kind of step back, the little slope field segment lines kind of give like a directional map for how the curves should be moving, right? So this is where the slope field is very helpful. It gives you a sense of what the antiderivative would look like. Again, don't worry about vocabulary words right now. I'll give you all the vocab you need, okay? So that's the whole point of a slope field. It gives you like a whisper of what function has a derivative that is blah. All right, Scroll down with me, not to the next page of your document, but to this problem right here. Right here. Here we go. Okay. So here's what I want to have you do, everybody. Right now, it says you're given this differential equation. Okay, notice now this differential equation, it has both x and y. On the axes provided, sketch a slope field for the given differential equation at the 12 points indicated. And these 12 points here, right? 1, 2, 3, 3 by, so these 12 points right here in bold, okay? And what you're going to want to do, obviously, for maybe let's just do that question together. You're going to want to evaluate, let's see, dy dx at that point 1, 3. At that point 1, 3 is going to equal, I'm just kind of trying to get some room for myself here. Well, at 1, 3, I'm going to get this equal to 2, right? So because I plugged in 3 for y, so when I go and put my little slope segment here, I'm going to go over here. I'm going to aim for a slope of 2, and sometimes I use my other points to help me, so it should be pretty steep. So boom, there's my slope field segment at this point. Go ahead, please, and complete the slope field for the rest, and then replay me. All right, very good. So here's my slope field. In case you're curious, right? These have a slope of 0. These have a slope of 0. These 2 points right here, this one and this one, those slopes are 2. These 2 slopes are 1, and these 2 slopes are -1. Why is that little thing here? I think I may have sneezed there. Okay. All right, very good. You know what? I want to share with you some little helpful hints. When you look at this dy dx, it's very obvious to me that when y equals 1, dy dx equals 0. When y equals 1, dy dx equals 0. All these points right here have y equaling 1. Just go right ahead and go 0, 0, 0. Similarly, if x equals 0, dy dx equals 0. Boom, 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 right? Okay, that's very helpful. All right, very good. Part B, while the slope field in part A is drawn at only 12 points, it is defined at every point in the xy plane. Describe all points in the xy plane for which the slopes are positive. I'm going to pause you there and just you're going to tell me in words, how would you describe all the points in the xy plane where the slopes are positive or where dy dx is positive? Go ahead and try that one. Okay, this is by inspection. I think you can see that dy dx is going to be positive for all points where y is bigger than 1, because if y is bigger than 1, this factor is positive, and as long as x doesn't equal 0, because if x equals 0, well, the slopes of the line tangents are 0. Well done, everyone. Okay, now flip back one page. Let's go over here. Another different kind of exercise in the kind of arena of slope fields. Oftentimes you'll get a matching question. This is a great question. This is, I think, the second page in your packet, okay? Go ahead and take a look at this. Here is a slope field question where they're saying they want you to match the slope fields, they gave you 5, with the correct DiffyQ. DiffyQ is short for differential equations. Everyone at the party knows what DiffyQs means. If you walk into a party and say differential equations, that's like you walking to a party and saying, I am laughing out loud, when I know full well your generation would say, I am LOL. So y prime, there's usually this notation, y prime, what does that mean, everyone? Y prime, yes, y prime is just another way of saying dy dx. Okay, let's all just right now meet up and just talk about which DiffyQ has to match, which slope field must match D. Let's talk it out and kind of use some just logic and try and make our life easier for myself. I'm looking at dy dx equals 1 over y, and it's clear to me that if y equals 0, dy dx will be undefined. If y equals 0, dy dx is undefined. Undefined dy dx means what kind of a tangent line? Either non-existent or the tangent line is vertical. Look at the slope field in graph 3. All the points right here where y equals 0, which is any point in the x-axis, notice right here, look at all those vertical tangent lines, yeah? So this right here, graph 3, is DiffyQ-D. Go ahead and see if you can match up A, B, C, and E, and then replay for the answers. There you go. There you go. B, A, D, we knew. E, C. Okay? All right, everyone, that is it for this screencast. The next part of your homework is to go ahead and do that one matching question that I posted on Canvas. It's step number 2. And don't forget, you do have a 20-minute quiz on Monday. All right? Do not feel the need to finish this packet. Don't worry, I will revisit this packet when I see you on Monday. All right, goodbye, everyone. Great job.